Now we can conclude the first order circuits if you understand a few more points. These are some miscellaneous but very important points. So we have defined the time constant only when dealing with the source free circuits. And at that time, what did we define? We defined it as the time taken for source free circuits. I'm talking about. For source free circuit, the time taken to fall to 36.8% of initial value. Okay, but for a step response, here it is the time taken to reach the 63.2% of final value. Why is this the case? If you remember the graphs for source free circuit, it was an exponentially decaying curve. Okay, but for a step response, how was the curve? It was like this. Okay, so considering a zero initial value, the final value whatever is there, to reach, let us say this is some current I naught, let us say. Okay, this is the current value. Now in order to reach 63.2%, this is 0.632 I naught. This time will be tau. And here what will happen? If you are taking I of t, this is the initial value, then at tau this reaches 0.368 of the initial value. Okay, so why is the difference coming? Because you can remember that here it was, the expression was I naught e to the power minus t by tau. Okay, so e to the power minus tau by tau, that means e to the power minus 1 will give you 0.368. And what about in the step response? Here it was I naught 1 minus e to the power minus t by tau. So here this will become 0.368. So 1 minus 0.368, you're going to get 63.2. Okay, so the time taken to reach 63.2% of the final value. Finally, the only thing that you have to remember is, if you see the exponential term, the denominator, there will be a ratio here, right? T by something or t into something. So whatever is in the denominator, that we will take as the time constant. If you see for RC circuit, tau is equal to RC, and for RL circuit, time is equal to L by R. If you do the dimensional analysis, so this is ohms, units is ohms, and this is in farad, but this you can get into the basic units. Okay, and if you get into the basic unit terms, you will get second. R into C dimensional analysis will give you second. Similarly, L by R will give you second. Okay. Now, sometimes what happens is, even if you have only inductors, you will have a second order circuit. For example, if you take, let us say this is a voltage source, and here you have inductor, and here you have another inductor. So this is L1 and this is L2. Okay, so now you can see that these two you can convert into an equivalent inductance. Okay, so if you're looking through these terminals, you will get L equivalent is equal to L1 parallel to L2, which is L1 L2 by L1 plus L2. Okay, so this will form a first order circuit. But now consider the case where here you have a resistor, here you have an inductor, and here you have another resistor and another inductor. Now, in whichever way you see, you cannot combine both of them. These two inductors cannot be combined to get an equivalent inductance. Okay, so this is L1 and L2. So if you look through the open circuited terminals of this inductor, there will be another inductor here. Similarly, if you look through the open circuit terminals of this, in order to find the Thevenin's resistance, you will have this inductor. Okay, so in this case, when you cannot get the equivalent inductance, then there will be two storage elements. So this will become a second order circuit. Okay, similarly for a capacitor, just replace this with a capacitor. When there are two capacitors in series or parallel, then if they can be replaced by an equivalent capacitance, then it will be a first order circuit. But if it cannot be replaced, like in this case, then it will become a second order circuit. Now what will happen in second order circuit? You will have two different time constants. Okay.